Okay, 110. Good afternoon. Hope everyone is doing good and ready for the weekend. I posted announcements on both the lecture and the lab website. Hopefully, students have had a chance to take a look through those. There is a homework reading assignment, and there's a homework due over the weekend, like Sunday. And then Monday, we'll have a short quiz. We haven't gone into a lot of material, but it'll be based on the material that we covered today, and then just a little bit recap that we did on Wednesday. Okay. So let me start with that one slide about the recap. So let's see. 15 recap. Okay, unit prefixes. As engineers, we work with a very wide range of values. Sometimes they are minuscule, very, very small. Sometimes they are very, very large. So we use the SI unit system, and then we use unit prefixes along with them to actually indicate the actual value of that quantity, right? So you might be familiar with most of the terms that are there in the center of the table, right? You'll be familiar maybe from high school, maybe from your first year, second year classes. Tell me this is not the first time you're seeing these, right? So what I want you to do is memorize this entire table. Nah, I'm kidding. Even I don't have it memorized. This is a handy dandy table. Again, when you are an engineer, you'll be working with other engineers, maybe managers from very wide different fields. And so they'll be, sometimes they might say, petabytes of data. Well, what is petabytes? Right? Byte is a digital word, and peta is the unit prefix, stands for 10 raised to 15. Okay. So if somebody says petabytes in a meeting, then it's on you as a engineer to know what is being talked about, right? So that's why I have this unit prefix table. Now, give you an example of how how small and how large these numbers are. Everybody is familiar with a meter and a millimeter, right? Millimeter is 10 raised to minus 3. Millimeter is, well, approximately this one. Every scale, every ruler has that 1 millimeter. It's 10 raised to minus 3 meters, meaning 1/1000th of a meter, right? If you take that millimeter and divide it into a further 1,000 parts, you get what is known as a micron, the Greek letter micro. The earliest semiconductor devices were on the order of microns. Okay, so they came up with this. It was very convenient for them to come up with a term that would describe 1 into 10 raised to minus 6 meters. Okay, 10 raised to minus 6 is very commonly or technically known as micron. If you take that micron and divide it into a further 1,000 parts, you get 1 nanometer. And that's basically the current scale of semiconductor devices. Okay, that's how small we're talking about. So that's the feature size. If you have used a mechanical pencil, you would have either 0.5 millimeters or 0.7 millimeter diameter. 0.5 is 500 microns, that thing. A human hair is on the order of about 75 to 80 microns. Okay, very thin. So 1 nanometer is, we can't even imagine. I've been working with these for a long time, and I still can't fathom how small it is. Okay, and then we go all the way down on the pico, femto, and atto. Typically in EE and CPE fields, we would see values going under the pico and the femto range. Well, that's incorrect. Should be 10 raised to minus 15. Typically for small parasitic capacitances, we would say picofarads or femtofarads. That's 10 raised to minus 12, 10 raised to minus 15. Very, very small. On this side, kilo, mega, giga, tera, you've all been familiar with just common common general knowledge, right? You would see megahertz, gigahertz frequencies, kilobytes of data, megabytes of data, gigabytes of data, and now we have hard drives and SSDs. They're in terabytes of data. Huge data centers work with petabytes and exabytes of data. Huge numbers. So someday you might be working as a computer engineer somewhere and be handling data centers or data in these amounts. To give you an idea of how big these are, how much is this? 1 mega. 1 million, right? So the simple exercise, take a wild guess at how much is 1 million seconds in days, weeks, months, or years. If you know the answer, just wait. But if you don't know the answer, just take a wild guess. 4 days. That's a good guess. Anyone else? Any wild guesses is fine. 5 years. That's okay. That's a guess. Anyone else? It's less than 12 days. It's 11 point some 7 or some days. Okay. So if you have $1 million and you spend $1 every second, you're gonna run out in less than 12 days. Now here's a billion seconds. How much do you think this is? 11,000 days. Well, it's true. It's 31 years. That's the difference between a millionaire and a billionaire. And the elite of the elite, there's about 1,000 billionaires. If you have $1 billion and you spend one every second, still be well settled for like more than 30 years. Anyway, just to point out how just a one order of magnitude, like going from like 10 raised to 3 or 10 raised to 6, 10 raised to 9, exponential multiplication. Okay. But regardless, the point is that you should at least be familiar with the middle of the table. These are the most commonplace unit prefixes that you will encounter as an engineer. Okay. All right, so let's get started with semiconductor fundamentals. All right, so the beginning of every lecture, there are some course, outcomes, meaning when we finished either with the topic or with the lecture or with the chapter, there are certain outcomes that students should use to self-verify. Meaning after you're done with your homework, you come back and look at these outcomes and verify whether you have learned to satisfy these outcomes. Okay, so today we're going to look at semiconductors. We're going to look at how semiconductors are created. We're going to start at the smallest level possible, atoms and subatomic particles, electrons, protons, and neutrons. All right. So this course, as I stated on the first day, is about applications, right? Circuits and electronics from a systems approach, systems-based approach. So we are more interested in the applications. EE students, they study this for an entire academic year. That's what I did. That's what I teach. That's a lot of EE students. Not a lot. Every single EE student has to do this. Okay. And so we compress it in the sense we are doing snorkeling. We are not going scuba diving, right? We are doing snorkeling. We're skimming the surface. So we start with a basic understanding of how semiconductors are formed, but then we'll quickly transition into the actual device and how we can use that device to create different systems, different circuits. Okay, so we'll devote a couple of chapters to semiconductor fundamentals and then move on to applications. So major applications of semiconductor devices, well, pretty much every modern electronic device or electrical device runs on semiconductors, right? We have it in our pockets, we have it at our fingertips, we have smartphones, tablets, mobile phones, television sets, even greeting cards in the last decade or so have like a small microchip in there. Like sometimes you have greeting cards that can record and play back a message. Sometimes there are pre-recorded messages, some jingles. And so that has a microchip in there that is pre-programmed. Okay, so there are semiconductors are around us everywhere. So in this course, we'll study something known as a diode, a transistor, which would be a BJT, and then a special type of transistor known as FET, field effect transistor. And the most common one of a FET or type of FET is the MOSFET, metal oxide semiconductor. Okay, metal oxide semiconductor, MOSFET. And MOSFET devices and transistor devices also come in two flavors. There's an N channel and there's a P channel. Okay, we'll look at that later on in this course, but this is just a broad overview. And if you create a microchip, or if you create a circuit which has both N and P type, or N channel and P channel MOSFETs, you get what is known as complementary MOS, or more commonly known as CMOS. And CMOS technology is what drives every semiconductor device nowadays, at least for the last few decades. Once MOSFETs were introduced, they determined a way to fabricate these devices. It exploded. It quickly took over the entire market. This is around the 70s and the 80s, and then just exponential leaps in technology. And now we are talking about like billions and billions of transistors, all on the size of a pinhead. Okay. So this is a diode. Diode is the most basic of semiconductor devices. It is a two-terminal device. It's marked here. Transistors and FETs are three terminals. There are four-terminal devices also. The origin of these devices, or the predecessors of these devices, were the vacuum tubes. Okay, there are vacuum tubes. So in a vacuum tube, you had electrodes. You had two electrodes. There was one electrode known as the cathode. There's another electrode known as the anode. And they're sealed inside a small glass tube, hence vacuum tube, right? There's a vacuum inside. And then the cathode is heated with a filament. It gets so hot that it starts emitting electrons. These electrons float on the surface of the cathode. If you apply a polarity to the anode and to the cathode, let's say you apply a positive polarity to the anode, what happens to the electrons? Electrons have blank charge, negative charge. And if you apply a positive potential difference to the anode with respect to the cathode, the electrons are attracted to the cathode, current starts flowing through the tube and the external circuit. Okay, so it's a one-way device. And the name came from the fact that it had two electrodes, diode, two electrodes. When they came up with the semiconductor version of the device, the name carried over, and hence it is still known as a diode. But it doesn't have any actual electrodes in there, just terminals. So major applications of a diode, the most common application is to convert AC into DC. That is known as rectifying or rectifier circuits. And again, we will look at all of these in detail. To do the reverse or invert from DC to AC, we use transistors. Okay, transistors. So AC to DC is known as rectification. DC to AC is inversion or inverter. You have studied inverters, logic inverters, maybe not. Okay, so this is a different, same word, same English language word, but completely different device. Okay, that is a logic inverter, not gate, meaning you give an input, it inverts it to the output. This inverter is basically related to power. So power electronics, DC is converted to AC. This circuit, where have you seen this? An application of this? Battery backup, yes. Vehicles. Many vehicles nowadays come with a 110-volt outlet. There's an inverter in there. My car is about 15 years old, so I don't have that. So I had purchased a separate inverter for about $40 a few years ago. I mean, several years ago. Yes. Kia Rondo crossover. It's like a micro van, but it's lasted me a long time, and I hope it continues. Nothing as exciting as my motorcycle. All right. The other application is an amplification, where we take a small signal. This, by the way, is the symbol for a microphone. Not very common. That's the technical symbol for a microphone. You take a microphone like this one, the signal is very weak. It converts the acoustic sound waves into electrical signals. That electrical signal travels, and this is amazing, it travels wirelessly via Bluetooth, which is just RF radio frequency, into the computer via the USB port. The computer receives the signal. Then, because the signal is weak, it needs to be made stronger. It needs to be amplified. And that's where we use amplifier. And that amplification can only be done with a 3-terminal, 4-terminal device like a BJT or an FET. Okay. BJT or an FET. And again, we'll talk more about all of these topics later on. So then we can use transistors and FETs and MOSFETs to implement digital circuits. Everything that we do nowadays is either digital or analog circuits. Some of them are mixed signal electronics. But when we say logic circuits, we are exclusively talking about digital circuits. Okay. So digital circuits, which is the binary number system, 0 or 1. 0 or 1. So we can use transistors, transistor devices to implement digital circuits. This basically is a subset of a digital circuit. A memory storage device is a digital circuit. Okay, so number 5 application is a subset of digital circuits. And this right here, which is solar cells, can convert photons, or we can take energy from photons and transfer it to electrons. And so that's basically converting light into electric. Solar cells. Now, all of this is made possible due to a specific type of material. Materials can broadly classified based on their ability to conduct electricity. Based on the ability to conduct electricity, they can be broadly classified as conductors, insulators, and semiconductors. Okay, conductors, insulators, and semiconductors. Metals have the property that they have luster, kind of shiny, malleable, they're ductile. You can make many various shapes and purposes depending on your application out of these metals. Okay, they conduct heat. They are excellent conductors of heat and excellent conductors of electricity. To conduct electricity, there are electrons that are orbiting the nucleus. In metals, the electrons they are loosely bound to the nucleus, so they are free to move around. And when electrons move, charge is moving. And when charges move, we say current is flowing in a circuit. Okay, so metals, good conductors of electricity, hence conductors. Then there are non-metallic elements, which are basically very poor conductors of electricity. There is no ideal conductor in real life. There's no ideal conductor. There is no ideal insulator. Okay, these are all in real life. A conductor will have a limit, have a limitation, right? How well they can conduct electricity. What is the best conductor that you know of? Silicon would be a semiconductor, but I heard gold, copper, copper wiring, can make PCBs from copper boards, um, aluminum to an extent. So again, they're all, depending on the material properties, they are either really good conductors of electricity or they might be somewhere in the middle. Gold by far is the best, one of the best conductors of electricity. So oftentimes you'll see, if you've ever seen the backside of a CPU, there are gold bond pads. That's there because they can last a very long time without like rusting, without degrading. And in the small amounts that is used, it's pretty much negligible. The cost is not that much. Okay, and then we have semiconductors. Semiconductors are from column 4 of the periodic table. Now I'm talking about semiconductors that are in their natural state. Okay, natural state, meaning inherent ability, which is column 4 is right here. And the most common ones we know of is silicon. Silicon, germanium, they are two of the most common ones. The earliest known prototypes of a diode and a transistor were made out of germanium. Okay, but silicon has some properties that make it very, very suitable for manufacturing of semiconductor devices. So the all right, the fabrication of semiconductor devices is an entire specialized field by itself. Okay, you need specialized fields, specialized equipment and expertise to fabricate microchips. Very few companies in the world actually build microchips, which is the most famous one, even though it's not doing so good now. Intel. The name Intel comes from integrated electronics. That's where it came from. Intel came up with the x86 architecture way back in the 70s. There's a long history. I love to talk about that history, but we don't have enough time within the confines of lecture time. So anyway, then a group of researchers and engineers broke away from Intel. They started AMD, Advanced Micro Devices. The original group actually came from IBM, and they came from the original inventors of the transistor. So there's there's a group of people at the top, and then they broke away, did something else, then they broke away and did something else. And today we have Intel and AMD. Intel and AMD, and to a certain extent, there's Texas Instruments, there were a few companies in Japan, Samsung in the last few decades. These are the only companies that design their own chips and manufacture them. Manufacturing is also known as fabrication. Okay, so you need silicon and silicon wafers to actually fabricate them. Now, AMD spun off its fabrication business, like Global Foundries. And then when Taiwan was trying to enter the semiconductor market a few decades ago, they thought we can never catch up with the designing. So let's just focus on custom foundry fabrication. And so all across Taiwan, you have these specialized companies that just fabricate, meaning manufacture semiconductor chips. Each equipment to process one single step costs millions of dollars. Okay. And a single floor can have like 10, 15 of these machines. So there's 100 million on a floor. 100 million in a room. There could be like 10, 15 rooms on a floor. So there's like $1 billion on one floor itself. So to start a company or a factory requires at least 20 to 30 billion dollars, and it takes about 4 years to bring it online. Okay. The reason I'm talking about all of this is that's an avenue where you could end up working. There's these are corporations that you could end up working. Okay. It also happens to be my specialization. These are silicon diodes and transistors or resistors that were made by Cal Poly students right here on campus. Okay, so I'm going to pass these around. Start one on this side and start one on this side. The diameter of these wafers is about 4 inches. This is from an actual production silicon wafer. Wouldn't do that. That's brittle. These are processed, but they're safe to handle. So these are 8-inch wafers. So production wafers are 8-inch, 12 inches. The larger the production, larger the size of the wafer, the easier it is, the lower the cost of the wafers. Okay. So these are actual silicon wafers. There's a clean room on campus at Cal Poly. We teach a class every winter where students come in, they learn, they go through the steps, and they learn fabrication or semiconductor fabrication processing. Anyway, coming back to our slides, if a semiconductor is created out of one single material, we call it a single intrinsic semiconductor, which is from group 4 or column 4. We can also create semiconductors by making a compound from 3 and 5. Okay. So if you use 2 materials to create a semiconductor, then make sure you don't drop them. Okay. If you drop them, it's going to shatter. So if you take and create a compound, it's known as a compound semiconductor. Could be from column 3 and column 5, could be from column 3 and column 4. So that's binary. And then if you have 3 materials, then it's ternary. Excuse me. These right here are these intrinsic or compound semiconductors. How many elements are in there? 2, more than one. So it's compound semiconductor. So compound semiconductors are created from typically depending on the purpose. Here's an example of a diode that is made from a binary, compound semiconductor. So the first one is gallium arsenide. Next is gallium arsenide phosphide. Next one is gallium phosphide. Last one is gallium nitride. You might have come across gallium nitride recently in the last few years, talking about fast chargers, right? The mobility speed of these semiconductors is very high compared to silicon. And so it's used in fast chargers and stuff, high frequency applications. These diodes, there's nothing special about these. These are diodes, but these diodes, normal diodes, when energy is transferred, get hot. They release some of the energy as thermal energy. So they release heat. They get hot. Semiconductors will release heat. These will release heat, but also, more importantly, they will let off light. Hence the name light emitting diode, LED. And so these are the LEDs that you may have used in the labs. And then, of course, we have LED. These are not LED lights yet, but several places on campus, when they're refurbishing, they're now installing LED lights everywhere. It's basically a compound semiconductor made up of different materials. Okay. And now we have tunable light bulbs where you can change a property and you can have whatever color you want from your LED. All right. So, yes. Okay, the question being asked is what processes are used to create these devices? That question basically is like, describe this field. It's a very good question, but it's so photography. That's what we use. So the technical name of the process is known as photolithography. Anyone ever see a photographer's darkroom, maybe a video or a picture where a photographer is like trying to develop some film and is like drying and shaking this piece of paper trying to get an image out, right? So what it was we had film cameras, right? When you when you open the shutter, you're allowing light into the camera, right? So there was unexposed film inside the camera, and when the light hits that film, now the chemical properties of the film store the image that it's seeing, okay, because of the available light. So now that film is going to hold that permanently or until its lifetime. So when you go into a dark room, you're going to take the film and you're going to put it in a machine, and you're going to put your photo paper underneath, now shine a light through that film. That film acts like a mold, and then when the light goes to that film, it's going to go and transfer that image onto your photo paper. The photo paper has chemicals that react with this UV light, and then you take that photo paper and you wash it in a chemical solution. So whatever is exposed stays on the film, and whatever is not gets washed away. And so it's liquid chemical, so you take it out and you're trying to dry it, and then you can have your, now of course it's all printed and it's different technology. But that process is known as lithography. That is what we use in fabrication of semiconductors. We have these glass masks that store patterns on them, and then we take a UV light source and we stick our glass mask in there that has patterns. Light is shine on it, light passes through. We have our silicon wafers that are sitting underneath that mask. We coat it with photoreflective material, not photoresist material. And then when the light goes through the mask, it's blocked in certain areas where it's transparent, it goes through, it exposes the photoresist. Then we take our silicon wafers and we stick it in chemicals, wet chemical, and it washes it away. So we wash it away, we wash it with water, we dry it with nitrogen, and the pattern is transferred onto the wafer. Okay. The process of doing that, the photolithography process, that's the smallest feature size. That is the most critical aspect. There's very few companies in the world that actually build those machines. Hence ASML. ASML is one of the big ones. They are the ones who supply pretty much every company around the world. So everybody wants to get their hands on ASML, and TSMC has the most advanced technology in fabrication. So again, if you have been dealing with world economics and politics, you know how important that that is. Anyway, so that's one of the basic steps of semiconductor processing. So let me ask you this. What is this right here? What element is that? Carbon is also in column 4 of the periodic table, yet carbon is not considered a semiconductor. Right? Carbon is not a semiconductor. Carbon occurs in nature in many various forms. Most common are graphite and diamond. Okay, graphite and diamond. So carbon under very, very high pressure and temperature forms a stable bond between its atoms, and that is a diamond. Very hard, indestructible material. However, a pressure a little bit this way or that way, and it's, instead of being crystalline diamond, it now becomes amorphous graphite. Okay. There is a process by which we can create diamond in the lab. Has a gas, typically methane, in a vacuum environment that contains carbon. It decomposes under the right pressure and temperature, control conditions. It it settles down and forms a diamond on a silicon wafer. I actually have one of those wafers that has like a 2-micron thick film of diamond. I'll bring it to class like maybe next week or something. Anyway, so carbon is not considered a semiconductor. Why? It's because there is something known, there is a there is a second property that must be satisfied. And that is known as the energy band gap, or the band gap energy. Okay, band gap energy, or the energy band gap. It's measured in electron volts. It's basically a measure of how strong the electrons are bound to the nucleus. Okay, so electrons cannot exist in random levels. They're orbiting the nucleus. So the theory, quantum theory, is basically that it cannot exist randomly. It has to occupy a certain state based on its energy level, right? So depending on how closely or how tightly it's held with the nucleus, there's an energy level that is described. So we call one of those bands as the valence band, which is the outermost shell, outermost orbit, right? The electrons in the valence shell. And then there is a conduction band. Those are simply referring to the energy levels, okay? The energy levels. So if the electron is in the valence shell, It's orbiting around the nucleus. It has energy. The energy that is required for the electron to move up from the valence to the conduction level, and the difference between those is known as the energy band gap. Okay, and that energy band gap for a semiconductor must be less than 3 electron volts. Okay, what is that? Must be less than 3 electron volts. For carbon, it is about 5.1 or 5.3. It's greater than 5. So for silicon and germanium, it's approximately or less than equal to 1 or 1.1. For carbon, it's in excess of 5.3. And so that band gap, that gap between the energy levels is insurmountable, not at normal room temperature pressures. Okay. And hence carbon is not a semiconductor because the electrons cannot acquire sufficient energy to break free. All right, let's take a pause, think over all of that. Let me know if you have any questions. Yes. Mm-hmm. To be honest with you, I actually don't have much experience with that. I had several peer students when I was in grad school who were working with graphene, carbon nanotubes, and this was quite a while ago, like in the 2000s and early 2010s. And so, yeah, I don't have much experience with that, but I'll look up an answer for you. Just remind me next class to bring it up. Yes. So the question is, does the band gap energy make the LEDs different colors? The answer is kind of yes, because the material property is different. So yes, it is different band gap, but that's because the material itself is different. And so we are using different materials, and because of different materials, and there's something known as doping or impurities that we'll look at in just a few slides, that we have different colors. It changes the band gap a little bit, and then it allows conduction of, sorry, it doesn't change the band gap. Sorry, that's wrong. Band gap is a material property that doesn't change. It changes the voltage that is required to overcome the potential. All right, so let's go here. Let's go all the way down to 0 Kelvin. Have you heard of 0 Kelvin? See? That is known as absolute zero, meaning it is so freaking cold, I can't move, I can't think, I can't do anything, I can't do jack. Everything's frozen in place. So if you are a silicon atom, silicon atoms have 4 electrons in the outermost orbit. To form a stable structure, one silicon atom bonds with 4 neighboring silicon atoms, and they each share 1 electron with each other. So if you take this top left right here, it has 4 of its own electrons in the valence shell or the outermost orbit, plus it has 4 neighboring atoms that share 1 electron each. So it has 8. Its neighbor also corresponding has 8. And so all atoms have 8 electrons. They're all stable. They're bound to the nucleus. There's not enough energy. There's not enough energy for it to break free. Okay. As I said, this is at 0 Kelvin. These bonds are known as covalent bonds, and these bonds are not broken at 0 Kelvin. Okay. So if the bonds are not broken, that means the electrons are occupying a certain spot. They are not free to move. If they are not free to move, they are not free to conduct electricity. Okay, so at absolute zero, everything's frozen. There's no free electrons. As the temperature starts rising from 0 Kelvin, right, we're going higher up. 10, 20, 30, 40, 50, 100 Kelvin, 200 Kelvin. Thermal energy is imparted to the structure. Electrons absorb this energy. The structure absorbs this energy. And some of these covalent bonds are broken. And when some of these covalent bonds are broken, electrons are free. They have acquired enough energy to break the bond, and they're now moving around freely in the lattice structure. And they can respond to an externally applied electric field. Okay, they can respond to an externally applied electric field in theory. So this occurs around 100, 200 Kelvin or so. So you have electrons that are broken free of the bonds, and they are now, excuse me, moving around in the structure. For every electron that breaks its bond and moves out, what is left behind? An empty space, empty spot, and you're right, it is known as a hole. And as one electron moves into a spot, so let's say there is a spot created here. Electron, oh, let's start here, 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 here. Okay, so let's say these were all occupied with electrons. Okay, and there's an electron here, electron here, electron here, maybe another electron here. So there's a spot to the left of this electron, the first one. It could jump into that empty spot. We can't control it. That's just part of physical nature. Okay, so it's moving to the empty spot. Now, when that electron moves left, it creates a hole right here. So electron moves here, and the hole is moving towards the right. So now there's a hole to the left of the second electron. That electron could jump and move into its spot, and thus the hole has now moved one more spot to the right. And then it propagates throughout the structure. As empty spots are created, more and more electrons could jump from spot to spot. Okay, it could just happen in a random, haphazard fashion. But the point is, as the electrons are occupying space, the holes are also being created at the same time. So electrons are moving. At that same time, we can consider the hole to also be propagating. And so the purposes of analysis and entire semiconductor theory, we treat the hole as a particle in its own right, and we say it has positive charge. And the reason it is said to have positive charge is when an electron moves out of a spot, the positive charge is bound in the nucleus. So the hole is bound to that nucleus. It is said to have positive charge. And so in semiconductor theory, we treat or we analyze with two subatomic particles, electrons which have negative charge, and holes which are said to have positive charge. What is this? It's interesting. All right, any questions? So you have electrons and we have holes. Yes. They're just moving around. They're there for the party. They just don't know what to do. So this, yes. So the question being asked is, are the holes closer to the nucleus or are they far away? Well, we are talking about the electrons that are in the valence shell. So it's the outermost shell. And the electrons that are in the outermost shell are the ones that are moving away. So probably the farthest state from the nucleus. No, it could move to another atom that has an empty spot. Again, that would be in the outermost orbit. Yeah. Yes. It's a good question. So, the question being asked is, do the electrons that are free and moving around break more covalent bonds? The answer is yes, under certain conditions. Not in this case, but when you apply an external electric field, there's an avalanche of carriers that go through. And because there's an avalanche of carriers that go through, they can impact other electrons and move them out of the spots. So more carriers are created, more free electrons are created. And that is basically the operating principle behind a Zener diode, which is, again, what we'll see later on in this chapter. Was there any other questions? Okay. All right. So this is known as an intrinsic semiconductor. Okay. Because it has free electrons at room temperature. There are not sufficient. There are free electrons, but they are not sufficient enough to count as a conductor. Okay. Hence a semiconductor. And both holes and electrons move through the lattice structure to conduct electricity. So there are some equations that govern this. The solid state electronics, solid state device physics is, again, an entire course by itself. And there are several equations, but we're going to look at one of the most basic ones. The N refers to the number of electrons. And the P refers to the number of holes. Okay. My best guess is N refers to negative and P refers to positive. That's the only thing that makes sense. Okay. So N and P basically refer to the number of electrons and the number of holes. For every electron that is available for conduction, there is a corresponding hole that is created. So at any point in time, the numbers are always equal. N is always equal to P. Okay. And the subscript I stands for intrinsic. It is inherent to the material itself. Okay. It is inherent to the material itself. Hence, intrinsic semiconductor. There is no other external factor affecting it. Okay. So it's intrinsic semiconductor. The only energy that an intrinsic semiconductor acquires is thermal energy. Compared to 0 Kelvin and compared to 300 Kelvin, which is 27 degrees C, the amount of electrons that are created can be described with this expression right here. Okay. That expression is NC times NV, sorry, root, excuse me, square root of NC times NV. And E raised to minus half EG over KT. So let's take a look at these three terms. EG is the energy band gap. Okay, band gap energy. That is a material property. Silicon, germanium, carbon, any material we take that has a band gap energy. Okay, and those are given right here. Okay. The NC and NV are the number of density states. Okay, number of states. So recall just a few minutes ago, I stated that electrons cannot exist anywhere. They have to occupy a certain energy level. Those energy levels are quantized. Okay, they are fixed. And each one of them is known as a state. So the number of states in a cubic volume of 1 centimeter, okay, 1 centimeter cube, is known as the density of states. So if you're talking about the valence band, meaning electrons that have valence, they are in the valence shell, they have valence energy. There are these many states present in 1 centimeter cube. present in 1 centimeter cube. Okay, that's the density of states. That's a material property. So these three numbers for germanium, for silicon, gallium arsenide, they hold true for under most conditions. Okay, so again, it's a simple plug and solve equation. Eg is a constant. Nc, Nv would be a constant. K is the Boltzmann's constant. You can either use joule, excuse me, joules per Kelvin or electron volts per Kelvin. Make sure you use the right unit prefix. And then T is the temperature in Kelvin. Okay, so we have Boltzmann constant, joules per Kelvin or electron volts per Kelvin multiplied by temperature in Kelvin. And then electron volts up there, energy, band gap energy, and multiplied with Nc times Nv. Okay, this is important that they're material dependent quantities. Okay. All right, it's past 2. It's 2:01. So we're going to end class here today, and I will see you all on Monday. Remember, there's a homework that is due on Sunday. There's an assigned reading, so you'll have to read a little bit, do the homework. If you get stuck anywhere, send me an email. I'm available over the weekend, so I'll answer your queries tomorrow. Saturday is a little bit tight for me, but Sunday I should be able to, yeah, answer queries if you need. All right, thank you. Who has my other wafers? Thank you.
This one you can see it says Cal Poly on it. If you look really close.
Yeah, it does have in the mask.
You know what that?
Hold on, let me.